In this video, we'll try to understand how the resistance depends upon the change in length and change in area of cross section of a particular wire. We know that the resistance expression is given by R is equal to rho L by A. Okay. So from this, what we can understand is the resistance of a wire depends upon the resistivity of the material with which the wire is made, the length of the wire, as well as area of cross section of the wire. Now we want to know what is the small change in resistance for small change in length as well as for small change in area of cross section. In order to understand that, for that equation R is equal to rho L by A, apply log on both sides. So we are applying log, means logarithmic function on both sides. So when you apply logarithm on both sides, we will get log R is equal to log rho plus log L minus log A. Here we used two different formulae for logarithms in order to get this expression. One formula for logarithm is log of AB is equal to log A plus log B. This is the first formula we used. Another formula we used is log of A by B is equal to log A minus log B. Of course, we have not written the base 10 here. Logarithm has a base value of 10. I have not written that here. Now, what I am trying to do as a next step is to differentiate on both sides. Okay, so differentiating on both sides. Why I am differentiating is I want to know what is the small change in resistance for small change in length and for small change in area of cross section. That's why I am differentiating on both sides. When you differentiate on both sides, the differentiation of log R is 1 over R dr. It is equal to, here rho is a resistivity which depends upon nature of the material and temperature. It has nothing to do with the length of the wire and area of cross section of the wire. Therefore, if you differentiate log rho, you will get 0. Next, going for the second term, which is log L, the differentiation of log L is 1 by L dl minus differentiation of log A is 1 by A dA. Okay. Now, in these two, if we consider only one change, either the change in length or change in area, the another term will become 0. Okay. So what I want to say is, if I am changing only the area of cross section of the wire, maintaining the length as constant, then this will be equal to 0 when I am changing area. When the area of cross section is changed, then dl becomes 0. So 0 into anything is 0. 0 into anything is 0. Now this will be true, means this will be a non-zero value, when means this will be 0 when we are changing only the length but not area of cross section. Therefore, when length is changed, when the length of wire is changed, maintaining the area of cross section constant, then when length is changed, then dA will be equal to 0. 0 into anything is 0. Now, considering the two effects separately, 1 by R dr can be written as 1 by L dl. Replacing this dr and dl with delta R and delta L, which are small changes in resistance and small changes in length, we get the change in resistance by original resistance is equal to change in length by original length. So this is the relation that we'll get. And the second relation is, considering only the change in area but not the change in length, you can have a separate relation which is 1 by R dr is equal to minus 1 by A dA. Replacing dr and dA with the delta R and delta A, you will get delta R by R is equal to minus delta A by A. So these are the two separate relations for the change in resistance when there is a small change in area of cross section, as well as when there is a small change in length of the wire. Okay. In the next video, we will see the situation when the wire is stretched or drawn or twisted. This is the situation when the wire is under with normal dimensions. We have not twisted the wire, we have not drawn the wire, and we have not stretched the wire. We consider the wire as it is. Okay. So I hope this video is clear for you. If you have any doubts in this video, please post them in the comment section so that we will try to answer them in our free time. Thank you very much.